Welcome to this explainer. Today, we're diving deep into the evolution of software engineering. We're going to take Professor Rita Salvi's course notes and turn them into a totally clear conceptual roadmap of exactly how we structure and execute modern code. Seriously, if you're looking to solidify your object-oriented principles or just kind of peek under the hood of Java's runtime environment, you are absolutely in the right place. Let's get right into it.
Here's our agenda for today. We'll be mapping out programming paradigms, looking at the shift to OOP, breaking down the core concepts of OOP, exploring Java's platform independence, and finally, going inside the JVM architecture.
Kicking things off with Section 1, Mapping Programming Paradigms.
So what exactly is a programming paradigm? And honestly, why do we have so many of them? Well, a paradigm is really just an approach, right? A methodology to solve a problem. Think of it as a master strategy that dictates how a specific programming language is put together. Historically, we've got four main types that guide software development: procedural, object-oriented, functional, and logic and rule-based paradigms. And what's cool is each one gives you a completely different lens for viewing a problem.
Before we jump straight into OOP, it's definitely worth highlighting functional programming. This paradigm is great because it beautifully avoids changing states and mutable data. It relies on what we call pure functions. Basically, that means the exact same input always yields the exact same output with zero hidden side effects. That makes the code super testable and just absolutely fantastic for things like parallel processing.
Then there's logic programming, which is a totally fascinating approach. Instead of micromanaging the computer and telling it exactly how to solve a problem, you just give it the facts and the logical rules. That's it. The system then uses an inference engine to figure out new knowledge from those existing facts. If you've ever dug into the foundational concepts behind early AI or natural language processing, you've actually seen logic programming working its magic.
Moving right along to Section 2, the shift to OOP.
You know, historically, as programs started growing from these tiny little scripts into massive enterprise systems, older methods just began to crack under the pressure. I mean, the continuous struggle in computer science is managing complexity, right? In procedural programming, the whole emphasis was heavily on the algorithm. It used this top-down approach where large programs were chopped into smaller functions, but crucially, data just moved openly around the system. It was totally exposed. Object-oriented programming flipped this entirely. It takes a bottom-up approach, binding data and functions together into objects, and it uses secure access specifiers like public, private, and protected to really lock down and protect that data.
So the big takeaway here is that OOP wasn't just invented for the fun of it. It was really the hero that saved large-scale software development. By breaking down incredibly complex software systems into manageable individual objects, developers could suddenly reuse code. They could easily update modular parts of a system without bringing the whole thing crashing down. And honestly, most importantly, they could finally start modeling their software after actual, real-world entities. Game changer, for sure.
All right, Section 3, Core Concepts of OOP.
Professor Salvi's notes brilliantly sum up the core philosophy here. We use classes as blueprints or templates, and then, from those blueprints, we create objects. Those objects are actual instances of the classes, and they pack in both the attributes, meaning the data, and the behaviors, which are the methods we use to manipulate that data.
To make all this work, OOP leans on four main pillars. First up, encapsulation. You can think of encapsulation as a sort of protective force field around your data. It makes sure the internal details of an object stay completely hidden from the outside world, only exposing what's absolutely necessary. This stops other parts of the program from accidentally messing with sensitive data, which, as you can guess, vastly improves your security and overall code organization.
Next on the list, we have inheritance. Honestly, this is a massive time saver. Inheritance lets us build on top of existing code instead of reinventing the wheel every single time we need a new, slightly tweaked object. So, if you've got a general vehicle class, your new car class can just inherit all those base vehicle traits. That means you only have to write fresh code for the specific stuff that makes the car unique.
Then there's polymorphism. Now, that might sound like a bunch of intimidating jargon, but it literally just translates to many forms. It allows objects from entirely different classes to be treated as if they were the exact same thing, responding to the exact same method call, but in their own unique ways. This makes your code incredibly flexible and way more adaptable to changes down the road. Finally, we've got abstraction. This is what helps us deal with the sheer, overwhelming complexity of modern software. It lets us interact only with the high-level features we actually need. It's kind of like driving a car, right? You know how to turn the steering wheel and hit the gas, but you don't need to understand the complex thermodynamic physics of a combustion engine just to run to the grocery store. Abstraction does exactly that, but for our code.
Moving on to Section 4, Java Platform Independence.
So Java is this high-level language built from the ground up by Sun Microsystems to perfectly execute all these object-oriented concepts we just talked about. But what truly put Java on the map is its unique compilation journey. When you write code, you save it as a .java file. But instead of compiling that directly into machine code for one specific computer, the Java compiler turns it into intermediate binary bytecode, a .class file. This right here is the secret sauce behind Java's famous write once, run anywhere capability.
And that compiled bytecode brings us straight to the Java virtual machine. The notes describe the JVM perfectly. It's a machine within a machine. By using this virtual processor, Java makes sure it genuinely doesn't matter if you're running Windows, macOS, Linux, whatever. As long as your device has a JVM installed, the JVM will interpret that universal bytecode into the exact machine language your host platform needs.
And that leads us to our final section, Section 5, Inside the JVM Architecture.
Let's pop the hood and look at the nested structural relationship of the Java environment, just to see exactly how it processes our objects and handles memory. The outermost layer is the Java Development Kit, or JDK. That's what developers actually use to write the code. Inside of that sits the Java Runtime Environment, the JRE, which provides all the necessary libraries. And nestled right there in the dead center is the JVM. That's where the actual execution magic happens. Diving a bit deeper into the internal subsystems of the JVM itself, when you run a program, the class loader subsystem is first up. It brings your .class files into memory, verifies them, and then pushes them right into the runtime data areas. It's basically prepping the stage for the execution engine waiting at the bottom. From there, the JVM meticulously organizes its memory into specific runtime data areas. The heap is super vital for OOP because that's where all those objects we've been talking about are dynamically allocated and stored. Meanwhile, the stack is holding on to the local variables for individual threads. The method area stores the structural blueprints for your classes. And the PC register, that's keeping track of exactly which instruction the machine is executing at any given millisecond. It's an incredibly tight system.
Finally, the execution engine steps in to actually run the code. It uses an interpreter to read the bytecode and a just-in-time compiler, or JIT, to speed up repeated sequences. But the feature you should really care about here is the garbage collector. By automatically scanning the heap memory, finding objects that aren't being used anymore, and just deleting them, the garbage collector completely saves developers from the absolute nightmare of manual memory leaks. It's a total lifesaver.
As we wrap up this explainer on the evolution of code in Java architecture, I want to leave you with one final thought. By utilizing paradigms like object-oriented programming to manage our own human complexity and ingenious architectures like the JVM to manage hardware constraints, we've automated away so many of the hardest parts of computer science. With these incredible foundational tools at our disposal, the only real limit to what we can build next is our own imagination. So, what are you going to build? Keep exploring, and thanks for joining us on this one.